Welcome for the today's lecture. Yesterday we have discussed the topic based on mutual information, and at the end of the lecture I told you that we would be solve one of the problem based on that. But today I have decided, first of all, I would be take one of the topic related to the Shannon's theorem of channel capacity, and then if time permits, okay. So I start with the topic of channel capacity. So how fast we can, there is a one question would be arise related to channel capacity, that how fast we transmit information over the communication channel. We have learned the information rate, we have learned the Nyquist criteria, noiseless and noisy channel, all the things. But can we answer how fast can we transmit the information over a communication channel? So the solution is that first of all we have to be remember about the information rate. Then and then only we can decide the speed of transmission of this information over the channel. So if you would be recall, we have learned the information rate where, for example, you can suppose a source sends small r messages per second. Here the variable small r is taken, that we are sending per second. Small r messages per second we are sending from the transmitter into the channel, and the entropy of that message is h bits per message. So in this way we can calculate the information rate is r into h, that is bits per second, means we can transmit rh bits per second, that much amount of information per second. So this is our information rate. Now we would be establish a relationship between this information rate and the channel capacity. So actually for this the Shannon has given uh, some theorem. So we know that according to Shannon's theorem, a given communication system has a maximum rate of information C, that is also known as the channel capacity. Means a channel capacity is nothing but the maximum rate of information. So your information rate would be either less than or equal to the channel capacity. So if you see, if the information rate is R and it is less than C, then one can approach arbitrarily small error probabilities by using intelligent coding techniques. If information rate is less than channel capacity and you want to send the information that is having the probability, small probability of occurring error, for that you have to be use some intelligent coding techniques. So there are lots of the coding techniques are available. We have learned some of the channel coding techniques on the previous chapter, and some source coding technique we would be going to learn in the next upcoming lectures. So whatever either of that coding technique you would be going to use, that would be decrease the probabilities of error, but can't be completely eliminate. And it is only possible when your information rate is less than channel capacity. So to get lower error probabilities, encoder has to work on longer blocks of the signal data. We have learned the block coding where we have to be form the blocks for sending the data. So we have to make a longer blocks of single data to decrease the error probabilities. And this condition entails longer delays, higher computational requirements. If you would be increase the length of the block of the signal data, so it would be also impose the delay, and as well as you have to be required more computational requirement. Okay. So what actually the Shannon says? Shannon says if information rate is less than or equal to channel capacity, then transmission may be accomplished without error in the presence of noise. Even if there is a noise in the channel, you can complete the transmission without error or very less amount of error. And for that, the condition is that your information rate should be less than channel capacity. Unfortunately, there is no any constructive proof of this theorem, but which states that actually there is this particular statement says that there is very less chance of existing such kind of the coding technique, because there is no any coding technique or method has been developed yet that would be reach the information rate equal to channel capacity. So when you are talking R is less than C, it is okay, but when you are saying that R is equal to C, it is not possible practically, because there is not any coding technique is developed still which would be make your information rate equal to channel capacity. So you can say that Shannon's theorem is true for the condition R is less than C, but not there is not any existing proof that could be established that R is equal to C. And what happens if the condition would be reversed? Means if R is greater than C, means information rate would be become higher than the channel capacity. Then errors cannot be avoidable regardless of the coding technique you are going to use. Practically it is not possible, but if you can say a arbitrary condition that R is greater than C, then either of the coding technique you would be used, it does not eliminate the error. Error would be persist on the data. That's why we have defined R is less than or equal to C. So everyone note it down. That is equation 1. That would be further come into the work when we will be proceed that topic. Now there is another theorem we have to be learn, that is jointly published by the Shannon and Hartley. It is called as the Shannon-Hartley theorem. So in this particular theorem, we have to be consider a band limited Gaussian channel. Instead of using a general channel, we have to use a Gaussian band limited Gaussian channel that is operating in the presence of additive Gaussian noise. So this is a block that I have shown you. There is a input data, and in this particular channel, that is the Gaussian channel, band limited Gaussian channel, where we have to be see there is addition of the white Gaussian noise, and when both would be add up and it would be passed through the channel, it has to be passed through the band pass filter, ideal band pass filter, and finally the whatever the output would be came, it would be sent to the receiver section. So for such a condition, when we are working in the band limited Gaussian channel in the presence of the Gaussian noise, the Shannon-Hartley theorem states that in that condition, the channel capacity could be defined as C is equal to B log base to 1 plus signal to noise ratio. And this is your equation number 2 here also. All of you please note it down. Now, if you remember, this equation is similar to the equation that we have learned for the noisy channel. In the past lectures, we have learned the channel capacity formula for noiseless channel and the noisy channel. And this we have defined, equation number 2 we have defined for the noisy channel, where the signal to noise ratio would be come into the picture. Okay. And if you would be see in this formula, so C is the channel capacity, that is having the unit bits per second. B is your bandwidth, that is represented in hertz, and S upon N is nothing but your signal to noise ratio. That could be either represented in the linear form, that is unitless, and if it is represented in the decibel scale, so the unit is decibel, dB. Okay. So this equation is very much important. The channel capacity defined by the Shannon-Hartley, B log base to 1 plus signal to noise ratio. Now, if you have to be see in SNR, the parameter that we have to be take into the consideration, that is noise. So how to calculate the SNR means what? Signal power upon noise power. So how we calculate generally the noise power? So there is a mathematical formula for calculation of the power over the bandwidth. So here you can see the equation where the power is defined as integration, that is limit from minus B to plus B, that is the bandwidth actually, power spectral density. So we have to be write the noise power spectral density. So you have to be see in this way we can define the noise power N is equal to integration, the limit is minus B to plus B, this is N naught upon 2 into D of F, because bandwidth is nothing but a frequency range. So the derivative of frequency, and N naught is what? It is noise power spectral density. Power spectral density of the additive wide Gaussian noise that we have considered in the Gaussian channel. Okay. So in this way, you can calculate the noise power. That is one of the important element of signal to noise ratio. So when you would be calculate the noise power, it would be defined with the help of equation number 3, N is equal to N naught D. So when you would be integrate this, finally you have to be got this equation, N naught into B. N naught is the Gaussian noise power spectral density, and B is the bandwidth. Okay, bandwidth of the channel. So you can see here we have defined noise power also. Now we can rewrite the capacity equation, channel capacity equation. That is C is equal to B log base to 1 plus signal power upon N naught B. So if you have to be see here, there is a two important element when we have to be calculate the channel capacity. One is the bandwidth, another is the signal to noise ratio. Now you can also say that your channel capacity depends upon the two factors, bandwidth and signal to noise ratio. So there is a trade-off between the bandwidth and the SNR ratio. So channel capacity, as I have told you, it depends upon the two factors. First is bandwidth, another is the signal to noise ratio. So one by one, we would be see the effect of these two factors on the channel capacity, and we would be establish a trade-off between the bandwidth and the SNR to determining the channel capacity. The first parameter that we are going to consider here is effect of signal to noise ratio on channel capacity. So if you have to be see, if communication channel is noiseless, if the communication channel is noiseless, then we know that at that moment noise power is 0 because there is no noise. This is the ideal condition actually. At that moment, according to the formula of signal to noise ratio, SNR would be become infinite. If noise power is 0, so SNR would be infinity. And if SNR is infinity, so according to the equation of channel capacity, your channel capacity will tends to infinite. That means the noiseless channel will have an infinite capacity. Infinite capacity. So a noiseless channel always having the infinite capacity. Okay. That is actually the ideal case. Practically, it is not possible. But when we are considering the noiseless channels, you have to be remember your capacity would be become infinite because noise power is 0. So this is very good question for objective point of view also, MCQ. Now come to the second factor, effect of bandwidth on the channel capacity. Now consider some white Gaussian noise is present, means SNR is not infinite, means we are talking about the noisy channel. Now keeping the SNR at constant level, bandwidth would be now vary and bandwidth would be approach up to infinity. And then we have to be see that as bandwidth approaches infinity, channel capacity does not become infinite because noise power, that is we have already defined, N is equal to N naught into B, we also increase with the bandwidth. Here you can see in the formula of the noise power that we have already defined, N naught B, noise power spectral density into bandwidth, that would be contribute to the noise power. So as you increasing the bandwidth, at the same time your noise power would be also increasing, and noise power is in denominator of the formula of the channel capacity. So as bandwidth increases, simultaneously your noise power increases, that would be decrease the value or reduce the value of SNR. Even we assume that our signal power is constant, your SNR decreases, and if SNR would be decreased, your channel capacity would be become finite value. It would be never reach to the infinity. Okay, I hope all of you have understood and correlate the terms. If you have written the equation number 1, 2, and 3, then you can easily correlate the terms, whatever I have told you. But if you have not written the equation, then maybe you would be confused with the terminologies. So I hope all of you have already written the equation. So here we have seen when we increase the signal to noise ratio, or we have considered the noiseless channel. So at that time SNR is infinity, your capacity would be become, channel capacity would become infinite. But this is not happen with the other parameter bandwidth. If you would be make bandwidth infinity, still your channel capacity would be not become infinite. because noise power also increase with the bandwidth. So in this way, we can conclude that an ideal system with infinite bandwidth has a finite channel capacity. So you can use the formula N is equal to N naught B in the equation number 2. That is the equation of the channel capacity. That is C is equal to B log base to 1 plus S upon N. N is replaced by N naught B. So here we have to be just multiply S upon N naught and divide by the same factor S upon N naught in this particular equation. So you can see N naught upon S into B would be become one parameter. I would be come to later on. So what would be the equation now? You can see S upon N naught is the one of the term, or you can say it is a constant here because we are varying only bandwidth. So bandwidth is only variable here. So log base to 1 plus S upon N naught B. So this N naught B and N naught B is common here, and this S is also common here. So you have to know that if we write like this 2, so what it would be become? You can write like as x square, means whatever the power term inside the logarithm, that would be come into the multiplication to the log. The same thing we have to be consider here. Consider this is a constant term like this N naught B upon S. So it would be become what? To the power of this particular term. So it is written here. So equation would be in the equation number 4, we have written the channel capacity is equal to S upon N naught log base to 1 plus S upon N naught B into raised to the power N naught B upon S. So this term would become here. Okay. So this would be become a new equation. Now, as per the consideration of the variable bandwidth, you would be get a new equation for the channel capacity. Now you have to make the bandwidth infinite. It does not make the channel capacity infinity. It would be decreased to the finite level. Okay. So I hope all of you have noted down this up to the equation number 4. I proceed. So can we write, I'm just in continuous form of this channel capacity. So can we write like this? C infinity means channel capacity would be become infinite, and when it is possible, as per the consideration we are making, the bandwidth is infinite. So limit B tends to infinity, C, that is equivalent to the C infinity. But there is a one obstruction. We can see what we know, that one of the mathematical equation of limit, when limit x tends to 0, 1 plus x to the raised to the power 1 upon x is equivalent to the Neperian base E, whatever the base we use in the natural logarithm. Because same condition we have got in the equation number 4. That's why I am correlating the term with the formula of the Neperian base. Okay. So there also, if you have to see the equation number 4, the same term is coming. Log 1 plus this is x and it is 1 upon x. Okay. So there is a one of the mathematical relationship according to the formula of the Neperian base, where we can say limit x tends to 0, That is 1 plus x to the raised to the power 1 upon x is equivalent to the Neperian base E. Here x is nothing but s upon n naught b. Okay. Why I have written x tends to 0? It is a standard formula actually. And here we have considered bandwidth infinity. If bandwidth is infinity, mean x would come to 0. That's why we are able to correlate this standard equation with the situation we have reached to defining the C infinity. Okay. So now using the same standard equation of Neperian base, your C infinity would be become s upon n naught log base 2 of E. Neperian base. From the equation number 4 we have written this. Now it is equivalent to what? We know that log base 2 of E is what? It is equivalent to 1.44. It is equivalent to 1.44. So C infinite would be become 1.44 signal power upon noise power or power spectral density of the noise S naught. This is become very important relationship. This is the formula of the maximum channel capacity. This is the formula of the maximum channel capacity when we would be try to make bandwidth infinite. Practically, a channel capacity can't be increased having the value more than this, equation number 5. So all of you please note it down, the equation number 5. Okay. So this is very, if you have to be establish the trade-off between the bandwidth and SNR, that would be establish some truth regarding the channel capacity. So what is this? According to Shannon's theorem, maximum rate of transmission is equal to the channel capacity. It can't be greater than channel capacity. It could be maximum equal to channel capacity, but practically it is not even achieve the value of the channel capacity. So maximum information rate means R max. That would be equivalent to the C infinite, that is 1.44 S upon N naught, because this is the practical value of the channel capacity. Okay, so maximum information would be given here 1.44 S upon N naught. So this is the theoretical value of the channel information rate. Practically, it is very difficult to achieve because it is extremely difficult to have a transmission channel having infinite bandwidth. Practically, there is no chance that we have the infinite bandwidth. Okay. So that I want to convey you. Now, what the conclusion we have find out here? If you increase the SNR to the infinity, you would be get the infinite channel capacity. But if you would be make the bandwidth infinite, try to make the bandwidth infinite, it would be give you finite value of the channel capacity. So in this way, the Shannon-Hartley principle indicates that we may trade off bandwidth for SNR and vice versa, means SNR for bandwidth. Try to understood with the help of this example. Suppose signal to noise ratio is equal to 7 and bandwidth is 4 kilohertz. So what is the value of the channel capacity? Can anyone calculate? Signal to noise ratio is 7 and bandwidth is 4 kilohertz. So what is the value of channel capacity? Formula you have, C is equal to B log base 2 1 plus SNR. SNR is given 7. Bandwidth is also mentioned 4 kilohertz. Anyone, please tell me the answer. Anyone? Monali, what is the answer?
12,000.
12,000. Yeah, 12,000 bits per second. We know that unit of the capacity. Just put up the formula, 12 into 10 to the power 3 bits per second. Okay. Now, I would be change the value of SNR. I would be going to increase the value of SNR and decrease the bandwidth. Then tell me what is the value of channel capacity. Now, SNR is increased by 15. It is up reached to the 15, and bandwidth is decreased to 3 kilohertz. Then tell me what is the value of the channel capacity. We are varying both the parameters at the same time. One is increasing, another is decreasing. Bandwidth is decreased by the 3 by 4 times as compared to the previous. Means it would be decreased by the 25%. And SNR is increased by the 2 times, more than the 2 times. So what is the channel capacity now?
Same 12,000.
Same value. So what we have seen that even we have decreased the bandwidth and increased SNR, the channel capacity remains constant. So now what is the relationship is here? So with 3 kilohertz bandwidth, noise power will be decreased by will be 3 by 4 as large as the bandwidth of 4 kilohertz. So noise power you have decrease the noise power. When you decrease the bandwidth, your noise power will be also decrease, because we know that N is equal to N naught B. So if noise bandwidth is decreased by the 25%, your noise power would be also decreased by the 25%. Thus, to get the same capacity, channel capacity, so what to balance the SNR ratio, signal power would be going to increase because noise power is decreasing. To do balancing the SNR, your signal power would be start to increase, and it would be start to increase by the factor, that is 3 by 4 into 15 upon 7, that is 1.6. So now you can see, therefore 25% reduction is bandwidth requires 60% increase in the signal power. Then and then only you would be get the same channel capacity, or you would be able to balance the signal to noise ratio on the same level. So there is a direct relationship between the bandwidth and signal to noise ratio. That this is the trade-off between the bandwidth and SNR for determining the channel capacity. Now, everyone, please note it down this question, and I am also simultaneously turn on your chat box for attendance. The question is saying that a voice graded telephone channel has a bandwidth of 3.4 kilohertz. If signal to noise ratio on the channel is 30 dB, determine the capacity of the channel if the above channel is to be used to transmit 4.8 kbps of data. Determine minimum SNR required on the channel. Determine minimum SNR required on the channel. So there are two questions involved in the one question here. It is a very practical problem for the telephone channels. So tell me, first of all, the capacity of the channel from the given information. It is very simple question. We have 3.5 minutes we can solve it. First is channel capacity. Anyone who have solved this? Your bandwidth is given. Given parameters are B is 3.4 kilohertz, and SNR in dB, it is 30 dB. So what we have to be do according to our formula? Can anyone tell me? Those who are solving this. Kaveri, what we have to be do first to solve this numerical?
Yes, sir.
As per the given information, how you would be calculate the channel capacity?
काय नाही लेक्चर चालू
This is most of you are just came for only attendance. You are not attending the lecture actually. It is a very simple, straightforward question.
SNR dB is converted into SNR.
Yes. First of all, you have to be convert this SNR in dB into SNR, linear value of the SNR. So what is the SNR in dB? Formula that would be, it is signal to noise power, so 10 log 10 SNR. So it is 30 10 log base 10 SNR. That would be 300 would be cancelled, log base 10 SNR. So your SNR is equal to 10 to power 10 raised to the power 3. That is 1000. Now you have got the linear value of the SNR. You can substitute this value on your formula of channel capacity. So what is the formula of channel capacity? The value of the channel capacity is, if you have to be see, the value of channel capacity is what? This would be C is B log 2 1 plus SNR. Just substitute the value here. So 2.4 into 10 to the power 3 log base 2 1001. Calculate this, you would be got the value. So solve this numerical. In the next lecture I would be asked the answer to everyone. Okay. Okay. Thank you all of you for attending the lecture.